Born in the hearts of stars, helium is the universe's greatest paradox. It cools the frontiers of medicine and propels humanity to the stars, the invisible power of science.
Every time you let a balloon go, a piece of the sun escapes our planet forever.
Yeah, that is, it's quite the statement.
Right. Just let that sink in for a second. That is a direct quote from the source material we are pulling from today. It's a documentary strategy guide developed for a project called Atomic 118.
Which is a fantastic project, by the way.
Oh, totally. So today we are doing a deep dive into element number 2 on the periodic table, which is helium. Our mission for this deep dive is to unpack its cosmic origins, the surprising mechanics behind its everyday uses, and the silent, impending crisis surrounding a substance that most of you listening probably think of as, completely ordinary.
Yeah, it really does sound impossible when you first hear that quote.
Yeah.
You picture like a brightly colored birthday balloon, something so trivial, and you compare it to a raging, burning star.
Right, it feels like a stretch.
It does, but scientifically, that statement is entirely accurate. Hidden inside every single one of those floating balloons is a gas so incredibly valuable that modern hospitals, space agencies, and top-tier quantum physicists literally depend on it daily.
Which is just wild to think about.
It is, and what's fascinating here is the ultimate historical paradox of this element. Humanity discovered helium in the sun before we ever found a trace of it on Earth.
Okay, let's unpack that timeline, because I'm trying to wrap my head around the logistics of 19th century astronomy here.
Sure, yeah.
It's like discovering a brand new species of animal by looking at Mars through a telescope, only to realize decades later that it's been living in your backyard the whole time.
That's actually a pretty great analogy.
Thanks. But, if they didn't have a physical sample in a lab, how did they definitively know they were looking at a new element from 93 million miles away?
Well, we have to travel back to the year 1868. Two astronomers, Pierre Janssen and Norman Lockyer, were independently studying a total solar eclipse, and they were using a device called a spectroscope. Now, to understand how they spotted helium, we kind of have to look at how light interacts with atomic structure.
Right, the physics of it.
Exactly. When an element is heated up to extreme temperatures, like, in the atmosphere of the sun, its electrons get really excited and jump up to higher energy levels.
Right, and when those electrons eventually drop back down to their normal state, they release that extra energy as a photon, like a tiny particle of light.
Precisely. And because every element has a completely unique arrangement of electrons, the specific wavelength, the actual color of that emitted light, is entirely unique to that element.
So it's basically an elemental fingerprint.
That is exactly what it is, an elemental fingerprint. So Janssen and Lockyer are pointing their spectroscopes at the blazing edge of the sun during this eclipse, analyzing the spectrum of light, and they suddenly notice this mysterious bright yellow emission line.
The famous D3 line, right?
Yes, the D3 line.
So, let me guess. That specific yellow wavelength just didn't match the electron drops for hydrogen or carbon or oxygen or anything we had ever tested in a lab on Earth.
It didn't match anything known to science, period.
Wow.
Because no known element could explain this specific yellow line, they deduced that they had stumbled upon something completely unprecedented, a brand new element.
Just by looking at the light, that's incredible.
Yeah, and they named it helium, deriving it from the Greek word helios, which is the Greek god of the sun.
Makes perfect sense.
Right. And for nearly 3 decades, helium existed only in scientific observations from space. It was just this theoretical celestial gas.
It is so cool.
It really is. It remains the very first element in human history to be discovered beyond Earth before being found on our own planet.
That is a brilliant piece of scientific deduction. But that origin story brings up a pretty glaring question for me.
But
well, if it was first observed burning in the atmosphere of a star, how does it actually form? I know we're dealing with element number 2, meaning it's incredibly light, but it has to come from somewhere, right?
Yeah, absolutely. To understand its origin, we have to look at the stellar furnace. We have to dive into the mechanics of nuclear fusion.
Okay, lay it on me.
So, a small fraction of the universe's helium was created right after the Big Bang. But the vast majority of it is actively forged deep inside the cores of stars.
Right, where the conditions are just insane.
Insane is the right word. Inside a star, you have this unimaginable environment. The gravity is so intense that the core temperature hits roughly 15 million degrees Celsius.
15 million degrees. And you need that extreme heat and pressure to overcome the natural repulsion of atoms, right? Like the Coulomb barrier.
Yes, exactly.
Because if you have two hydrogen nuclei, which are basically just positively charged protons, they naturally want to repel each other, sort of like two positive ends of a magnet.
That is the exact mechanism at play. Under normal conditions on Earth, those protons would violently push away from each other.
Right.
But inside a star, the immense, just crushing pressure and unimaginably high temperatures force them together with such velocity that the strong nuclear force takes over.
Oh, I see.
Individual hydrogen atoms are violently forced to collide and fuse together to create a heavier element, which is helium. Element number 2. 2 protons, 2 neutrons.
But wait, fusing them together takes energy, doesn't it? How does that reaction actually power the star? Like, where does the heat come from?
That's a big question. It comes from the mass defect. This is described by Einstein's famous equation E = mc squared.
Ah, okay.
When those hydrogen nuclei fuse into a helium nucleus, the resulting helium atom is actually slightly less massive than the individual parts that went into it.
Wait, really? It loses mass?
A tiny fraction of the mass is lost, yeah.
Yeah.
But as we know, mass cannot simply disappear. It is converted entirely into energy.
Oh,
And that tremendous release of energy is the literal engine that powers our sun. It produces the light and the heat that make all life on Earth possible.
that's mind-blowing. So helium is essentially the ash left over from the nuclear fire of a star.
That's a very poetic way to put it, but scientifically, yeah,
Yeah.
it's the ash.
It's just staggering to think about the scale of that mechanism. I mean, for you listening, the helium we buy at the party store, the gas inside a simple Mylar balloon, was actually forged in stellar furnaces billions of years ago.
It really is ancient stardust.
We are using ancient stardust to make things float. But, okay, this is where the logic kind of hits a wall for me.
How so?
Well, if the vast majority of helium is being synthesized inside stars through massive nuclear fusion, how do we have it here? Earth isn't a star. We definitely don't have enough gravity to trigger fusion.
No, we definitely don't. The helium we harvest on Earth has a completely different geological origin story, though it does rely on similar atomic physics.
Okay, so where does ours come from?
It involves the dark depths of the Earth's crust. Most of the helium we have down here is generated by radioactive decay deep underground.
Radioactive decay, like uranium and stuff?
Exactly like uranium and thorium. Deep within the Earth's crust, you have these heavy, unstable radioactive elements.
Unstable meaning their nucleus is too large to hold itself together.
Spot on. They're slowly falling apart to reach a more stable state, and over millions and millions of years, these heavy elements decay through a process called alpha decay.
Alpha decay. Okay, what does that look like?
So the nucleus of a uranium atom essentially ejects a tiny packet of particles to shed mass. That packet, which we call an alpha particle, consists of exactly 2 protons and 2 neutrons.
Wait, 2 protons and 2 neutrons?
Yep.
That is the exact nucleus of a helium atom.
Yes, it is.
Yeah.
The alpha particle shoots out of the uranium atom, careens through the surrounding rock, and violently strips 2 electrons away from neighboring atoms so it can balance its positive charge.
Oh, wow.
And in that exact instant, it becomes a fully formed, completely stable atom of helium.
So it's basically underground atomic alchemy.
That's a great way to describe it.
Radioactive heavy metals are just naturally transmuting into the second lightest gas in the universe. But wait, if it's the second lightest element, why doesn't it just seep up through the dirt and escape into the sky?
Well, its natural tendency is absolutely to escape. To understand why it's so difficult to hold on to, we have to look at its electron shell. Helium is what chemists call a noble gas.
Right, the noble gases.
It has exactly 2 electrons, which perfectly fills its one and only electron shell. And because that shell is completely full, it is highly chemically stable.
Meaning it doesn't want to play with other elements.
Exactly. It is colorless, odorless, non-toxic, non-flammable, and it's one of the least reactive elements on the periodic table.
So it refuses to bond with anything. It won't react with the rock. It won't dissolve efficiently in groundwater. It won't bond with carbon.
Right. It simply doesn't want to form molecules. So because it refuses to bond, and because it is so incredibly light, it just migrates upward through porous rock.
Just floating up.
Yeah. And if it reaches the surface and enters the atmosphere, it just keeps going. Earth's gravity simply isn't strong enough to hold on to it.
It just floats away.
It floats up to the edge of space, the solar wind catches it, and it is stripped away into the void forever.
Wow. So here is where the logistics get really precarious for us. I mean, it's like finding a buried treasure chest, but the gold instantly evaporates if you don't catch it the exact second you open the lid.
That is a very accurate fear.
So how do we actually harvest an evaporating gas?
Well, the only reason we have a supply to use today is because over those millions of years, some of this upward floating helium hit a roadblock.
Okay, what kind of roadblock?
It encountered layers of dense, impermeable cap rock, deep underground, often massive salt domes or dense shale, basically the exact same geological formations that trap methane and natural gas.
Oh, so they get caught in the same pockets.
Right. The helium gets trapped, mixing in with the natural gas reservoirs. So today, when energy companies drill down to extract natural gas, they occasionally hit a reservoir that contains a small percentage of helium, usually less than 1%, actually.
Less than 1%, that's tiny.
It is. And to harvest it, they have to run the natural gas through a highly complex cryogenic separation process just to isolate that tiny bit of helium.
So unlike a chemical compound that we can synthesize in a lab by mixing two things together, this is totally different.
Completely different.
Nature takes millions of years to slowly cook this stuff up through alpha decay, and we cannot simply manufacture it on demand.
No, we cannot make it.
Yeah.
We can only extract what the Earth has been slowly trapping for eons. And when you realize how incredibly rare and difficult to capture this ancient gas is, the way we use it becomes a serious point of discussion.
Yeah, no kidding.
Because society relies on it for applications that are far more critical than party balloons.
Well, let's get into those applications then, because the Atomic 118 Guide maps out a massive industrial demand for this gas. And I think most people just think of blimps or, sucking it out of a balloon to change the pitch of their voice.
Right, the funny voice trick.
Exactly. So why are we going through complex cryogenic separation to mine an evaporating gas?
The primary driver of global helium demand is its unique thermodynamic properties. It is, quite simply, the ultimate cryogenic coolant.
The ultimate coolant.
Yes, because its atoms have such weak intermolecular forces, again, going back to it being a noble gas, it refuses to turn into a liquid until it reaches negative 269 degrees Celsius.
Negative 269.
Yes, that is just 4 degrees above absolute zero. It is the lowest boiling point of any element in the universe.
Wow. Okay, so what specific technology requires a liquid that ridiculously cold?
Superconducting magnets, the most vital example being the massive magnets used inside MRI scanners in hospitals around the world.
MRI machines use helium.
They absolutely depend on it. To make an MRI work, you need an incredibly powerful magnetic field to align the protons in the water molecules of a patient's body.
Okay.
And to generate a magnetic field that strong, you have to pump a massive amount of electrical current through coils of wire.
But wouldn't normal copper wire just overheat and melt from that much current because of electrical resistance?
Exactly. The friction of the electrons moving through the metal generates a ton of heat. But if you bathe certain specialized metal alloys in liquid helium, bringing them down to near absolute zero, this crazy quantum phenomenon occurs.
What happened?
They become superconductors. They lose absolutely all electrical resistance.
Yeah.
The electrical current can flow continuously without losing any energy to heat, creating a massive, stable magnetic field.
That is fascinating.
Millions of medical diagnoses, finding tumors, mapping brain injuries, they rely entirely on this technology. Without helium, modern medical imaging as we know it simply stops.
I don't think most people look at a giant high-tech MRI machine and realize it is fundamentally dependent on the exact same gas inside the balloon tied to a mailbox.
It is the exact same gas. But the applications extend way beyond the hospital too. Because it is totally inert, meaning it won't react or catch fire, and because it stays a gas at incredibly low temperatures, it is vital for space exploration.
How does space exploration use it? Just for weather balloons?
No, for the rockets themselves.
Really?
Yeah. When NASA or private space companies launch a rocket, they use liquid oxygen and liquid hydrogen as fuel.
Right, rocket fuel.
And those liquids are incredibly cold. As the rocket burns fuel, the fuel tanks start to empty out. You have to push a gas into the tanks to maintain pressure. Otherwise, the structural integrity of the rocket would just collapse under the forces of launch.
Ah, okay. And if you pumped, like, normal air or nitrogen into a tank of liquid hydrogen?
The nitrogen would instantly freeze solid into ice.
Ah.
Yes. It would block the valves and cause a catastrophic failure. Helium is the only gas that will not freeze when it comes into contact with liquid hydrogen.
So they use it to pressurize the tanks?
Thousands of gallons of it, yes.
Mm.
Furthermore, it's essential in semiconductor manufacturing. The silicon wafers in our phones and computers have to be manufactured in entirely pure, controlled environments.
Okay, I can see where this is going.
Because helium is inert and conducts heat exceptionally well, it is used to rapidly cool silicon during production without reacting with the microchips.
The source material also mentioned deep sea diving. What is the mechanism there?
It solves a major physiological problem called nitrogen narcosis.
Nitrogen narcosis.
Yeah. When professional divers go to extreme depths, the immense water pressure forces the gases they breathe to dissolve into their bloodstream and tissues.
Right, basic pressure physics.
Exactly. If they breathe standard compressed air, which is mostly nitrogen, the nitrogen dissolves into the lipid layers of their nerve cell membranes. Under high pressure, this causes an intoxicating effect similar to being drunk, which, as you can imagine, is incredibly dangerous underwater.
Yeah, that sounds like a nightmare. And helium prevents this.
It does. Because helium atoms are much smaller and significantly less soluble in human tissue than nitrogen, they don't dissolve into the nerve membranes the same way.
Oh, I see.
Divers breathe a mixture called trimix, which is oxygen, helium, and a little nitrogen, allowing them to work at extreme depths with a clear head.
That's amazing.
Add to that industrial leak detection. Helium atoms are so small they can escape through microscopic cracks that water or air cannot, making it perfect for testing the seals on spacecraft or chemical pipes. And of course, it's the backbone of advanced quantum computing research, which requires components to be isolated at near absolute zero.
Okay, so if I just map this out for a second.
Go for it.
We have doctors relying on it to spot life-threatening illnesses. We have engineers using it to manufacture fiber optic cables and microchips, astronauts needing it to launch rockets, and quantum physicists using it to unlock the secrets of the universe.
Right.
We know it takes millions of years to form through radioactive decay, and we know we cannot artificially synthesize it. And yet, I can walk into a big box store right now, pay $20, and buy a tank of it to blow up balloons that will just pop and release it into the atmosphere.
That's a stark contrast.
Are we basically using a vital, irreplaceable scientific resource as a cheap party trick?
Well, this raises a very important question regarding resource management. What you have just outlined is the central conflict of the source material. It is what scientists refer to as the quiet helium crisis.
Let's examine the reality of this crisis, because when we hear the word shortage, we usually think of oil or fresh water or lithium.
Sure.
But a helium shortage, if it's escaping into the air, why can't we just build giant atmospheric processors and pull it out of the sky? Like the same way we extract liquid nitrogen or oxygen from the air.
It comes down to basic thermodynamics and economics.
Okay, how so?
The concentration of helium in the Earth's atmosphere is roughly 5 parts per million.
5 parts per million, that's nothing.
It is astronomically dilute. To pull helium out of the air, you would have to cool and compress millions of cubic feet of atmosphere down to absolute zero just to extract a tiny vial of gas.
Oh, I see.
The energy required to run that refrigeration process would be infinitely more expensive than the value of the helium you'd recover.
So recovering it from the sky is a thermodynamic nightmare. And we can't just build a fusion reactor to make more, like replicate the sun.
No, not currently.
Yeah.
While experimental fusion reactors do exist, they currently require more energy to run than they produce. We are nowhere near synthesizing large commercial quantities of helium economically. We are entirely 100% dependent on whatever happens to be trapped inside underground geological vaults right now.
And meanwhile, the technological demands are just accelerating.
Exponentially. I mean, the global demand for MRI machines is surging as medical infrastructure improves worldwide. The space industry is experiencing a renaissance with more commercial rocket launches than ever before. Semiconductor manufacturing is expanding rapidly.
Yeah, that makes sense.
The demand for these advanced technological uses continues to climb, while the underground natural gas reserves that contain helium remain strictly limited and heavily subject to geopolitical supply chain disruptions.
So we have a rapidly rising demand for life-saving and futuristic tech, and a completely fixed, evaporating supply that we are simultaneously venting into space for decorations.
It's a tough reality. It forces us to ask how we balance everyday consumer goods, the undeniable joy of a floating balloon at a parade, with the absolute needs of advanced science and medicine. When we know the supply has a hard stop, it's not a matter of if we deplete easily accessible helium, but when.
Wow.
Scientists are warning that aggressive conservation, mandating the capture and recycling of helium gas used in scientific labs and hospital MRI suites, is no longer just a good idea. It is an absolute necessity.
It fundamentally changes how you look at the world. If I can synthesize the gravity of this for you, the listener, it transforms something incredibly innocent into something profound.
I completely agree.
A harmless childhood staple, a floating balloon, isn't just a toy anymore. It is a symbol of a massive, quiet scientific crisis happening right under our noses. It forces us to realize that just because a resource is invisible and just because it is economically cheap today doesn't mean it isn't infinitely precious.
It is a profound reality check on our relationship with the natural world and really our relationship with the cosmos. We are quite literally squandering pieces of ancient stars.
I think that is exactly where we need to land today. We have been on a vast journey with this one seemingly simple element.
We really have.
Just think about the life cycle of element number 2 that we've mapped out today. Born in the violent, blazing nuclear hearts of ancient realizing the atomic fingerprints in the light of the sun before anyone even knew it existed on Earth. Created deep underground by the slow, silent radioactive decay of heavy metals trapped under dense rock for millions of years.
And now, humanity extracts it to do the most amazing things.
Exactly. To chill superconducting magnets, to peer inside the human body, to pressurize the rockets, expanding our footprint in the cosmos, to build the quantum computers of tomorrow.
Only to watch it slowly escape back into the darkness of space if we fail to manage it.
It is an extraordinary story.
It truly is.
So if you are as captivated by the hidden mechanics of the universe as we are, I highly encourage you to follow and subscribe to the Atomic 118 Project. They are crafting amazing journeys, exploring the origins and applications of every single element on the periodic table, and this documentary strategy guide on helium was just a glimpse.
It's a phenomenal resource.
Please share this deep dive with your fellow science enthusiasts. Help spread the word about the importance of helium conservation. And if you enjoyed our conversation today, leave a review. It genuinely helps.
It does help. And I want to leave you with one final lingering thought to mull over as you go about your day.
Oh, I love these. Let's hear it.
The source material captures it beautifully. The next time you see a floating balloon, remember, you are looking at a piece of a star.
That gives me chills.
It makes you wonder, you know what other seemingly mundane